Hi, today I was going to make logic gates and circuits for you with relays, but then I realized you know nothing about relays to start with. So today is relay day. Let me make one for you. Here, this is similar to a relay, which is basically a switch. The spoon acts as the switch lever constantly pulled by a spring that connects this terminal called common to either normally closed terminal when unactuated or normally open when actuated. See, with such switch, I can turn on, say, a light bulb. See, when the contact moves... When there is live voltage exposed, you should stay away from live exposed metal at all costs. You can use rubber gloves or non-conductive material like a piece of stick to move things around. What the is this circuit? A switch goes in series with the power lines, not parallel. Maybe I should have just made relay logic. But no, today is relay, then you can learn the logic itself from my sponsor Brilliant. Brilliant is a website and app to learn many things about math, science and computing, like logic, with highly interactive courses where you learn it by doing it. So become way more productive using Brilliant and get 20% off of a year of Brilliant Premium membership using brilliant.org/ElectroBOOM. Now, with the proper arrangement, it should turn on. It should have been easier. This is a single pole because it has one common terminal. Dual throw switch because it can throw that one common over to two different terminals. There can be other types of switches like single pole, single throw, single pole, dual throw, dual pole, single throw, dual pole, dual throw. In a relay, the switch actuation is done by magnetic force that pulls the lever up, closing the... Magnets can be quite conductive. Let's try it again with a layer of insulation. There you go. And when I let go of the magnet, the spring returns it back to the normally closed position. In the actual relay, an electromagnet like this is used to actuate the relay. Like this. This is good because now the coil is completely isolated from the circuit it's switching. That's all. And this is an actual relay that if I put 12 volts across its coil contacts, you would be able to hear it click like this. Oh! Well, apparently we are not done because it shocks for a simple reason that it is a coil. I talked about inductors in my ElectroBOOM 101, but basically when you place a voltage across a coil, its current rises to some level and it stores electric energy in form of magnetic fields. When you disconnect the voltage, the coil will want to release its energy. The polarity across it flips and it tries to push the current through. But now there is no low resistance path for the current to flow, so the voltage across the coil rises so much that it arcs across the gap, shortening it so that the current can flow. Like this. Do you see the little arcs? So if I touch across the coil when I disconnect the voltage, I receive a shock if the coil is large enough, like in this relay. You see, I can make a novelty zapper with this. Quite simple. What I'll do is I connect the relay coil to the supply voltage on one side and to the ground through the normally closed contact of the same relay on the other side. What happens initially is that the coil is energized and so the relay switches, disconnecting the coil and creating high voltage across it. And the coil is de-energized so the relay switches back. So the relay oscillates like this. And in every cycle it creates a high voltage spike. Ow! Yes, it shocks. Oh, it's a harmless prank. So let's not go higher inductance than this. Oh, it seems like I'm getting short pulses of around 300 volts. Not as shocking as a 1000 volt, but whatever. But in our circuits, we typically use a transistor to turn the relay coil on and off, which means when it turns it off, the spike of high voltage will fall across the transistor and kills it. That's why we always provide a path for the current to flow, like a freewheeling or flyback diode. When we turn off the transistor, the coil current will flow through the diode, which will clamp the voltage and eliminate the high voltage spike and discharges the coil energy. So here I added a flyback diode across the coil that will clamp the voltage and make it absolutely safe for me to touch the hell? What the hell is going on? Oh yeah, if you have noticed, this diode must be reverse of the supply, so it's normally off until the coil pushes current through it. In my setup, I put it the other way, so it shorts the supply. Trying again with correct polarity. There you go. And now, it won't shock me at all. But as you can also hear, the switch is switching slower. Now, of course, with such a diode, when you turn off the coil current doesn't die right away and it flows through the coil for longer, keeping it on for longer, and so the relay switches slower. But there is a way to make the relay switch faster. We could add a Zener diode like this in series, like a 5-volt Zener diode. So when we turn off the coil and current starts flowing, there will be much larger voltage drop across these components. Times the flowing current will result in a much higher power loss that diffuses the coil energy much faster and the relay switches quicker. Here's a test with a single flyback diode. There, from the yellow line where the coil turns off to when the switch switches, it takes around 10 milliseconds. And here's the test with an addition of a 15-volt Zener. See? Now it takes less than 4 milliseconds to switch. The pulses you see on the relay switch is because of the relay contacts bouncing against each other when they switch. Fun! Now there's of course more stuff to consider about relays, like for example there's a maximum switching current, because like I showed, when the relay switches, the contacts bounce against each other and don't make proper contact right away. Or the contacts might have been oxidized and are initially higher resistance, so the contacts could overheat either by arcing when it's bouncing or through the contact resistance, and they could melt and fuse together. Like this, imagine your relay wants to connect a power supply to a circuit that has a large capacitance. See, the relay switches now. And if I connect the capacitor and try to switch the relay, see, the relay is stuck because the contacts are melted. Yeah, typically some good slapping disconnects the fused contacts. Until next time. So it's best to keep the current limited when you are switching the relay. And that's not all. You can only switch a voltage below a certain level for reliable switching. Of course, if the voltage is too high, the gap between the contacts will break down and an arc will short them. But that's not the only issue. The voltage may not be high enough for an initial arc, but if it is too high and powerful, when you switch to it and try to switch away, the arc between the contacts will not go away and will keep the contacts short. Here's my ZVS circuit that can create tens of kilovolts, but I can put the contacts at a distance that no arc jumps, like this. If I close between the contacts, I would be able to... If I short between the contacts carefully, there, it's maintaining the arc. Same thing happens to a relay. I'm gonna put 2000 volts across my man-made relay. Very dangerous, never try this at home. See, the voltage is not high enough to jump across the contacts, but if I close and open the relay, close and open, the arc doesn't go away anymore. The breaker popped. So if the high voltage and power is available between your contacts, the arcs may never go away and keep your contacts shorted or open after a long time, which can melt your contacts and damage your relay and short your circuits. Such high voltages can happen when you switch inductive loads, like I showed. So you must keep the switching voltage and current below the relay rating for reliable switching. Fun! But that's not all. Every relay coil is designed to switch the relay at a nominal voltage like 5 volts or 12 volts. But there is a minimum voltage called pickup voltage above which the relay is guaranteed to switch. After you turn on the relay though, you can maintain its state at even lower coil voltages. So to reliably turn off the relay, the coil voltage must go below the release voltage. And of course there is a maximum voltage above which you will overcurrent and melt your coil. See, this is a 12 volt relay, but it will turn on around 6 volts and turns off around 3 volts. But what if you have a supply voltage much higher than what the coil can handle? Easy. Instead of a continuous on signal, you give it a PWM to turn the coil voltage on and off. So fast that the coil doesn't have time to de-energize. Something above 1 kHz should be enough. With a proper PWM duty cycle, you can create an RMS voltage and current no more than the maximum power rating allowed by the datasheet. You can even regulate these by adjusting the PWM duty cycle for different supply voltages. And that's not all. For some weak and small relays, there needs to be a minimum contact voltage and current present. Like when you switch them, there is a recommended minimum load for reliable switching. Why is that, you ask? Let me show you. If you don't use your relay for long periods, there can be a very thin layer of oxide on the contacts that don't let it connect well, or in my case, it's soot.
Soot.
Here I'm trying to turn on a low voltage LED circuit, and because the contacts are covered in soot, it won't turn on, see? Is soot conductive? It's made of carbon. It could be graphite, so damn it! Maybe if I melt the contacts with my capacitor a bit. Again. Again. Does it conduct now? It doesn't. But if the voltage is high enough, like 120 volt AC, it is guaranteed to break through the oxidized layer. See? And that's why there is sometimes a minimum required switching voltage and current. And there you have it. Of course, there are some other parameters that are easy to understand, like the maximum operating temperature. And there are other type of relays too, like the latching relay or polarized coil or even the solid state relays that have their own benefits and disadvantages. But these relays will never go away, or at least as long as I live. Next lesson, I guess at some point, digital circuits with relays. But not before you learn logic, which you can learn from my sponsor Brilliant. My daughter and I spent hours solving the fun and challenging logic puzzles at Brilliant, which really teach proper and logical thinking and lead into arithmetic and computing logic. I just didn't expect her to solve those quicker than me. And Brilliant keeps releasing new courses that are even more interactive. Like the newly updated scientific thinking course, where you learn how to think like a scientist, learning a ton of science by doing scientific puzzles and reading their detailed explanations. Can you imagine being entertained by learning? That's what Brilliant is brilliant at. They understand that hands-on active problem solving makes it fun and is essential in learning complex concepts. If you're really looking into refreshing, improving, or even learning a new concept in math, science, or computing, look no further. Use my link brilliant.org/electroboom and enjoy 20% off of a year of Brilliant Premium. And thank you for watching.